Let's start off with sequences and series, and there actually is a subtle difference between a sequence and a series. So a sequence is just a set of numbers that follows a pattern. Sometimes called a progression, so you might see the term progression used sometimes. So that's a sequence, whereas a series is when we add those numbers together. Right? So the sequence, for instance, would be 2, 4, 6, 8, whereas the series would be 2 plus 4 plus 6 plus 8. So it's a subtle difference. The series has a plus sign in there. Okay, A, creatively, we use that for the first term. Don't know how we thought of that one. But then after that, we tend to go term N. I mean, you could use term 1 for the first term if you wanted to. Sn then would be the series, the actual answer to the series when we add them all up. So, for example, here's a general term. Our number pattern is n squared plus 2. We want to find what is the fifth term. It's just substitution, isn't it? Sub it in, 27. Well, is 42 a member of this sequence? Does it belong in the set? I mean, these are the sort of questions they sort of ask with these number pattern type questions. So, all right, well, can I solve this? Will this give me an answer? And it does give me an answer. However, remember, we're not dealing with continuous data here. We're dealing with discrete data where the answers are always integers for n. And square root of 40 is not an integer. So no good. Now, a recursive formula is another way of writing out the general term, but it writes it in terms of previous terms. And I guess a classic one is the Fibonacci sequence. So that particular pattern where we know any term is the sum of the two previous terms. So that would be a recursive formula for that pattern. So it'll always designate the starting term. So in Fibonacci, in fact, there's two starting terms we go off with, isn't it? The two starting terms is 1, 1. Then we'd get some expression to go, okay, now how you can work out all the other terms. So here's one where it's every term will be 3 plus the previous term. And we're saying, well, this formula would work for n is greater than or equal to 2. So I suppose in that Fibonacci example, that one would work for n greater than or equal to 3, because we had the two previous terms. And we're told the first term in this one's 4. So the first 4 terms, well, it's just a matter of keeping on adding 3. The Lucas numbers. So it's the same sequence as Fibonacci, but you'll notice the starting numbers are different. So the Lucas numbers start where the first term is 2 and the second one is 1. So it goes 2, 1, but then the next one would be 3, 4, and so it's going up and up. So remember, the first two don't satisfy the pattern, the recursive formula. So it's okay to have 2 and then go down to 1. I mean, that's still fine. It's still a pattern. We're really interested in two special series or sequences, the arithmetic ones and the geometric ones. So let's have a look at the arithmetic. Our definition for an arithmetic series. Sequence of numbers. Each term is found by adding some constant amount to the previous one. So it's a very simple pattern, and we creatively call that difference the common difference, and we symbolise it with D for difference. So the difference then, if I wanted to work it out, I could get term 2 and subtract the first term. I could get term 3, subtract the second term. I could get any term I like, really, and subtract the term before it. In fact, I don't really need consecutive terms, because I could have, what's an example? The 7th term and the 10th term, and I know there'd be 3 differences in between them. So the recursive formula for that would be, term n would be the previous term plus the difference. It really is just a rearrangement of that difference formula there. So that's the recursive formula for arithmetic. So let's create the general term then. First term is A. We're going to add a difference to it to get the second term. Add another A. Ooh, there's a pattern emerging. Yes, in fact, any particular term would be A plus n minus 1, lots of differences. Okay, so we're told the third term is 9, the 7th term is 21. What is our formula for this number pattern? So this is, like I was saying, you don't necessarily have to have consecutive terms. We have the third term, and if you're unsure how many differences, well, all right, you could create simultaneous equations. A plus 2D is 9. A plus 6D would be 21. So, oh look, there's 4 differences. And 4 differences would equal 12. So we now know the difference is 3. Sub back into our simultaneous equation. We can work out the first term for this one, 3, as well. The general term then, A plus n minus 1D. So sub in the 3's. And really, in this one, we've just ended up with multiples of 3. So 3n would be the formula for this number pattern. So what would term 100 be? 300. Which would be the first term bigger than 500? So in other words, when is that general term bigger than 500? So we just have to solve this in equation. But remember, we're talking about discrete data here. So 503, not good for us. We want the first integer that's bigger than that, which would be 167. It then brings up an interesting question. What is the answer to this question? It says, what is the first term greater than 500? So is it correct to simply say, oh, well, the 167th term would be the first term greater than 500? So I've sort of answered the question. I haven't actually said what that term is. I think it's safer to put both down. So let's work it out. It's 501. So term 167, which is 501, which would be the first term greater than 500. So if we were to plot all that discrete data, we should get a linear function. Makes sense, because think of the general formula, a plus n minus 1d. It's a linear function. 1a is not necessarily arithmetic ones, it's just number patterns in general. So don't try and use your arithmetic formulas to solve ones in 1a, whereas 1b is specifically arithmetic.